Hello everyone and welcome back. My name is Pradeep Kumar Wala and today we are going to deep into something that is happening right now at this very second on every device connected to the internet. Topic number 3, HTTP, HTTPS, TCP/IP and DNS. By the end of this video you will understand exactly how data travels from your device to the server and back, every layer and every step. And when you type the URL and press the enter, it will never feel like a magic again. You will know precisely what is happening. So let's dive in. Before we go deep, here is the roadmap for the today. First, the protocol stack. Think of it as a 4 layers, each with one job. Second, HTTP version. Why 1, 2 and 3 each were the revolution. Third, HTTPS and TLS, what actually makes your connection secure. Fourth, TCP, the most important handshake in the networking. Fifth, DNS, the internet's phone book. And sixth, we put all four together and trace exactly what happens when you type a URL. These are not separate topics, they are four pieces of one puzzle. By the end, you will see how they all click together. Look at this slide. 4 layers stacked on one of each other. This is protocol stack, and the easiest way to understand it is with a story. Imagine you are writing a letter to a friend in another country. You write the message, that is layer 4 HTTP. The what you are saying. You put it in an envelope and write guarantee delivery, return if lost. That is layer 3. TCP, the how it gets there reliably. You write the address on envelope, that is layer 2. IP, the where it needs to go. The postal truck physically carries it, that is layer 1. The physical layer. Wi-Fi waves, Ethernet cable, fiber optic light. Every time you load a web page, every single request passes through all four of these layers on the way out and then back through all four on the way in. That is the protocol stack. Now look at this three column. HTTP has evolved over the years and each version solved a real problem. Let me explain each one with an analogy. HTTP 1.1. Imagine a taxi, one passenger at a time. You hail a taxi, you arrive, taxi return, next passengers gets in. If you have 10 passengers, 10 separate taxi trips required. This is HTTP 1.1. One request at a time per connection. There is even a problem called head of line of blocking. If the first request is slow, everyone waits. HTTP 2. Now imagine a bus. Many passengers, one trip. This is multiplexing, multiple requests over one connection simultaneously. Plus, HTTP2 use binary instead of text. Machines read it 30% faster. And server push, the server can send you files before you even ask. HTTP2 is the standard today, used by about 65% of the website. HTTP3, this is the future, built on UDP instead of TCP. If one packet is lost, only one that stream is affected, not everything else. Better on bad network like mobile, Google, YouTube, Cloudflare already use it. The progressions tell you something important about engineering. We are always solving the next bottleneck. Look at the left side of this slide. Without HTTPS, your password travel is a plain text. Anyone on the same Wi-Fi, a coffee shop, or an airport can literally read it. Your password is visible as a plain text in a network traffic. Think about that. You are at Starbucks logging into your bank. Without HTTPS, the person at the next table with simple tool can see your password. With HTTPS, the same data becomes something like unreadable format. That little padlock in your browser means this encryption is active. So, how does it work? Through the TLS handshake. 5 steps that happen in about 100 milliseconds before any data flows. Step 1. Your browser say hello and tells the server what encryption method it supports. Step 2. The server reply with its SSL certificate, which prove its identity like showing a password. Step 3. Your browser verify that certificate was issued by the trusted authority. Step 4. Both sides agree on a shared secret key that nobody else know. Step 5. Encryption channel open. Now everything is scrambled. Every secure website, every bank transaction, every login, all protected by these 5 steps running silently in the background. Look at the diagram on the left. See those three arrows. SYN means synchronized. SYN-ACK means synchronized acknowledged. And ACK means acknowledged. This is the TCP three-way handshake. Three messages before any data flow. And this is one of the most important concepts in all of networking. Think of it like starting phone call. You call someone, SYN, hello, can you hear me? They reply, SYN-ACK, yes, I can hear you. Can you hear me? You confirm, acknowledge, ACK, yes, great, let's talk. Now the conversation begin, right? This three message ritual guarantee that both sides are ready, reachable and willing before single byte of real data is sent. That is the TCP's promise, reliable, ordered delivery. Now look at the table on the right. TCP versus UDP. Notice the trade-off. TCP is reliable, every packet confirmed in order, resent if lost. But it is slower because of all that checking, used for web pages, emails, file downloads, anything where every byte must arrive correctly. UDP is fast, fire and forget, no confirmation, no waiting. But packet can be lost, used for video calls, gaming, live streaming, where a dropped frame is better than freezing while you wait for resend. The rule of thumb, if accuracy matter, use TCP. If speed matters and occasional loss is acceptable, use UDP. Look at this slide carefully, 7 step, with the time each one takes on the right. This is what happens every time you type domain name and entire chain completes in about 50 milliseconds. Here is the problem DNS solve. Computer talk to each other using number. IP address like 142.250.8046. But human think in a names. Google.com, YouTube.com. DNS is the phone book that translate between them. Step 1. Browser cache. Have you visited google.com before? Your browser already saved IP address. Instant, no network call needed. Step 2. OS cache. Your operating system keeps its own DNS cache, still local, still fast. Step 3. Your recursive resolver. This is usually your internet provider's DNS server. It does the hard work on your behalf. Step 4. Root DNS server. There are only 13 root DNS server in the world. The resolver asks them who manage.com. They point the TLD server. Step 5. TLD server for .com. The resolver asks who manages google.com specifically. They point to the Google's own namespace. Step 5. TLD server for .com. The resolver asks who manages google.com specifically. They point to Google's own name server. Step 6. Google's authoritative name server. This is the final authority. It knows the exact IP address 142.250.8046. Step 7. IP returned and cached. Your browser know where to go. And the resolver cache this for everyone else who asks the next. Notice something beautiful. The first time is 50 milliseconds. Every time after that, it is instant from the cache. This slide shows 6 types of DNS record. You do not need to memorize all of them today, but knowing the main one will help you in both interviews and real engineering work. The A record is the most important one. A stands for address. It maps domain name directly to an IPv4 address. Google.com map to 142.250.8046. Every website needs an at least one A record. For A's, record is the same idea but for IPv6. The newer addressing system with much longer addresses. As IPv6 adopting grows, for A's record become more important. CNAME stands for canonical name. N alias. www.google.com point to google.com instead of having separate IP address for www. It just says same place as the main domain. MX record is for the email. It tells email server where to deliver mail for your domain. Gmail.com's MX record point to mail.google.com. TXT records are flexible text record used for domain verification, email security setting, things like SPF and DKIM that prevent email spoofing. In system design interview, you will often discuss DNS-based load balancing, having multiple A record pointing to different server, so DNS itself distribute traffic. Keep that in mind. This is the slide that ties everything together. Look at the 5 steps with the timing on the right. This is the full picture, all 4 protocols firing in a sequence. Step 1 DNS about 50 milliseconds. Your browser need to find where google.com lives. It goes through the DNS chain we just discussed. Browser cache, OS cache, resolver, root, TLD, authoritative, and return 142.250.8046. Step 2 TCP about 30 milliseconds. Now your browser need to establish reliable connection to that IP address. Three-way handshake. SYN, SYN-ACK and ACK connection ready. Step 3 TLS about 60 milliseconds. Because you typed HTTPS, the TLS handshake happen now. 5 steps to establish encrypted channel. Certificate verified. Encryption key agreed. Step 4 HTTP about 80 milliseconds. Now your browser sends the actual request. Get slash HTTP to host google.com. The server processes it, it queries its system and return 200 OK with the HTML. Step 5 render about 50 milliseconds. Your browser parses the HTML. Discover it needs CSS, JavaScript, images, font. For each one, a DNS lookup if needed. TCP connection, TLS if HTTPS, HTTP request. All these happen in parallel. Total about 270 milliseconds from pressing enter to page visible. 4 protocol, dozens of messages, thousands of kilometers of network travel. Every single time you open a web page, that is not magic. That is incredible engineering. Alright, 5 questions that come up again and again in interview on this topic. Question number 1. What is difference between HTTP and HTTPS? HTTP send data as a plain text. Anyone intercepting it can read it. HTTPS encrypt everything using TLS. The padlock in your browser means TLS is active. HTTPS uses port 443. HTTP uses port 80. In production, always use HTTPS. Question number 2. Explain TCP three-way handshake. Client send synchronize. I want to connect. Server replies synchronize acknowledged. Okay, I am ready. Client send acknowledged. Great, let us go. Three messages establish a reliable connection before any data flows. Question number 3, DNS and why does it matter in a system design? DNS translate domain names to the IP addresses. In system design, it enables powerful pattern. DNS round robin load balancing, failover by updating DNS record. CDN routing by returning different IP based on user location. Service discovery and microservices also uses DNS. Question number 4, TCP vs UDP. When would you choose each? TCP when every byte must arrive correctly, web pages, API, file transfer, banking. UDP when speed matters and occasional loss is fine. Video calls, live streaming, gaming, DNS itself. Question number 5. When you type URL and press enter. DNS lookup, TCP handshake, TLS handshake if HTTPS, HTTP GET request, server processes and respond, browser renders. This entire sequence in under 300 milliseconds. And that is HTTP, HTTPS, TCP/IP, and DNS. You now understand the actual plumbing of the internet, not just that it works, but exactly how it works layer by layer, step by step. If, if this video helped you, please like and subscribe. It genuinely helps in series reach more engineers who want to learn system design in the right way. Topic 4 is coming very soon. APIs, REST, GraphQL, gRPC, three completely different ways system talk to each other and when to use each one. I see you in the next topic. Thank you.